Hi everybody, I'm just going to make a video covering alkyne reactions since we aren't going to have a ton of time to talk about them in class the first day. But when we're thinking about alkyne reactions, we really want to be thinking about what our alkene reactions look like, okay? Think about an alkyne, so just something like this. That is an alkyne. Think of an alkyne like an alkene with an extra pi bond, right? So if you've got an alkene and it has one pi bond and then an alkyne has two pi bonds, you're going to have very similar reactivity between those pi bonds. But there are differences that we can take advantage of to give different types of products than just the alkenes. Okay, so we're going to think alkene reactions here. With a bit of a twist. Okay, so there are kind of three major classes of alkyne reactions of the ones that are really commonly used. There are a couple more in your book and we will talk about those briefly, but I'm really only covering the ones that are going to be different from the alkene reactions that you expect. The ones that act the same are in the book, and just think about the ones that are not in this group that I'm going to cover. They pretty much all work the exact same way as the alkene reaction, they just do it twice. Okay, so instead of doing one hydrohalogenation, it does two of them. Okay, but you can check that out in your book. So we're going to talk about hydrogenation, we're going to talk about hydration, and alkylation. Okay, these are things that are kind of unique to the alkyne functional group. So that's what we're going to be focusing on. All right, so for hydrogenation, hopefully we're familiar with that from last semester with the alkenes, where we would have something like this with hydrogen and palladium on carbon, or some sort of catalytic palladium, catalytic platinum, and then we reduce that to an alkane by syn addition of hydrogen. Okay, so we can do that same exact reaction with an alkyne. So if I have this alkyne and I say hydrogen and some sort of catalytic palladium, whether that's palladium on carbon or whatever you want to use, I'm going to go all the way down to the alkene. Okay, because the first thing I'm going to do is I'm going to make an alkene first by one addition of H2, and then that alkene will go and react just like it did up here and do another hydrogenation to get to the alkene. Okay, so this is added H2 two times. Okay, so if we want to stop at the alkene, that could actually be really useful, because then we have a whole new way to make alkenes from that. And we can actually do that by modifying the catalyst that we use. Okay, so if I use hydrogen gas just like before, and instead of using palladium straight, I can use Lindlar's catalyst. Okay, and Lindlar's catalyst is just kind of a reduced reactivity version of palladium. Okay, so there is palladium there, but it is a less reactive version of it. They call it poisoned. So it's not quite as reactive and not able to go past the alkene. Okay, but this is still chemistry that's happening on a surface. So you've got your hydrogens coming from the same side. So it is still a syn addition. Okay, so we're going to end up getting a syn alkene or a cis alkene. From that syn addition. Because Lindlar's is always going to be syn addition, just like hydrogen and palladium. Okay, So what if I want a transalkene? So if I want a transalkene, then I have to use a different set of reagents. So this reagent is, well, this reaction condition is kind of nasty. So it uses lithium metal dissolved in liquid ammonia. Okay, so this is called a dissolving metal reduction. We're not going to talk a ton about the mechanism here. It is a radical mechanism, which we have not covered yet. But it's because it goes through a different mechanism that it gives you a different product out of it, because it ends up wanting to hit that trans configuration. And so it falls into that as the lowest energy, and then it keeps on, keeps stuck in that throughout the reaction. So if you want to look at the mechanism, it is in the book. I'm happy to talk about it, but we haven't talked about radicals yet, so I don't want to go through too much and get it all confusing. Okay, but from these three reactions, we can have an alkyne turn into a transalkene, a cisalkene, or an alkene. Okay, so we have those three right there. And this is going to be transalkene. All right, so let's talk about hydration. So hydration is one that we talked a lot about for alkenes. We had three different methods that we used for alkenes. We had sulfuric acid and water. We had hydroboration oxidation. So actually, let me start that list over. So sulfuric acid and water, and then also oxymercuration, demercuration. Okay, both of those put the OH on the most substituted side, right? We saw that in the mechanism that we wanted to go for the most stable carbocation position. So that's where we would end up putting our OH. The other one we had was hydroboration oxidation, which is the one that puts the OH on the least substituted side, because we've got that big boron group coming in that wants to sit at the edge, and then that boron is replaced by your alcohol. So we're going to have very similar versions of those for the alkyne reactions. The really interesting thing about this is that it's not going to go quite as you would expect it to. Oh my gosh, sorry. The sweater is like really bad with this iPad. Okay, so this is actually going to be a way of making carbonyls. Okay, so in an alkene, you're making alcohols. For this one, we'll actually see that we're going to be making a carbonyl rather than just stopping at the alcohol. Okay, so because we're again dealing with kind of regiochemistry of, you know, which side of the alkyne does my OH want to sit on, this is going to be more useful for terminal alkynes. Okay, where we actually have a difference in substitution on each side, because otherwise we're going to get mixtures in internal alkynes. Okay, so up above with the hydrogenation, this can be internal and terminal alkynes, all work fine. Okay, the hydration reactions mainly are going to be for terminal alkenes. Okay, so let's start off by just using the simple one, so the water and the sulfuric acid. Okay, so we've got our terminal alkene. We're going to add water. We're going to add sulfuric acid. And this is what makes it slightly different. We're going to be adding mercuric sulfate. Okay. So we're going to have HgSO4. Okay. So what that mercury does is think about the oxymercuration, demercuration. The first step is creating that mercurinium ion, where you have the mercury is actually activating your alkene. That's what it's doing here. It's just acting as a catalyst to help that reaction move along, okay? So that's all it's there for. You can even think about it as kind of forming that little triangle intermediate. I'm not going to draw that out because it's, you know, it would look really horrible with the double bond in it. But that's essentially what it's doing. It's just activating the alkyne there to make the reaction a little bit easier to run. So from here, we're going to do a very similar mechanism that we've seen before. So our first step, we're in acidic conditions. So our first step better be protonation of our pi bond. Okay, so we're going to protonate first. That's going to form this really lovely situation. Okay, so now I've got a carbocation on my pi bond. So on a new alkene. This is a pretty reactive carbocation. It's better to put it again on the more substituted side than the less substituted side, but it's really, really not happy there as a pi bond and a positive charge at the same time. So very, very quickly, we're going to have our nucleophile come in. Our nucleophile is water. So we're going to come and attack that carbocation. I put that off to the side. It's unnecessary. Okay, so then we form this, okay? So this is a positively charged intermediate right now. Let's make it neutral. So to make it neutral, we just need to deprotonate what used to be water. And we're going to use water to do that. So water is going to be our nucleophile and our base. The sulfuric acid is going to be our acid. So make sure that we're not mixing any of those roles up. All right, so we're going to deprotonate. And then that gets us to this structure. Now, this is one of my favorite functional groups, just because I really like the name. So this is, oh my goodness, sorry. Okay, it's an alkene and it's an alcohol. So in their infinite wisdom, organic chemists named this the enol, okay? Alkene, alcohol, the combination of those two things together. Okay, so an enol is actually not a very stable functional group. It is very, very quick to tautomerize is the word. Okay, so that is forming the enol, and then the tautomerization. Actually, I'm just going to put it over here. Okay, I always thought that tautomerization was one of the most confusing things. I think it was really just because the word scared me because it was a big word. But tautomerization is just taking an enol to a carbonyl. Okay, so we're going to make this into a ketone in this case, because if we look at where the OH is, that carbon it's on is connected to two other carbons. This is going to turn into a ketone. So this is called an enol keto or a keto enol tautomerization. Okay, and we're going to see this kind of thing all throughout the semester. Okay, so we are currently in acid right now. We have not left the reaction conditions. We're still in the same reaction pot. So we're in acid right now. So that means I need to make sure that I'm only having neutral or positive charges on this molecule. So if we think about where we're trying to get to, eventually we want to be getting to a ketone. Okay, so I want that to be a ketone. So if I kind of take a look at what needs to happen, I need to add another H here to get to 3. And I need to take this one away, and I need to get rid of that pi bond. Okay, so if I'm in acid, that's going to be how I get my H onto the carbon. So let's first just protonate that alkene. Okay, so if I protonate that side, that means that I now have a carbocation over here. But that carbocation is right next to a heteroatom with lone pairs on it. So then we can do our favorite thing in the world, which is draw a resonance structure. I need to scooch this guy over a little bit. Okay, making sure that we're using our resonance arrows here, because this is resonance. Okay, now I just need another acid-base reaction, and I can get to my ketone. Just like that. Okay, so that is the tautomerization step from enol to ketone. Okay, so let's look at what we would get if we did a hydroboration oxidation. And I'm gonna scooch that on down. Okay, so for hydroboration oxidation, so we started off just using BH3 for our alkenes, right? You can sometimes get away with using BH3 on alkynes. So your book shows it that way. There are people that do it this way as well. It can be a little bit tougher though, because you know that BH3 can also react with alkenes. So that could be a little bit of a sticky situation. But one way to overcome this is by using a bulky borane reagent. So sometimes we'll use something like this. Okay, so if I have 2 of those, think about one coming off of the boron and another one coming off the boron, and then that one BH bond. Okay, that's essentially what we have going on. So this is bulky. And because it's bulky, it's going to have a very hard time connecting to much, really. But think about an alkyne is nice and long and linear. As soon as you get the alkene, you've got more stuff off of it. It's going to be less easy to approach. So this is pretty much only going to react with alkynes. Okay, and now it's even more clear which side that boron is going to add to. So we're going to want to match up our alkyne by putting all of this stuff out where it has plenty of space to roam. And then we're going to overlap our H with the rest of the molecule. So we're going to be making those 2 connections rather than the other way, where you're going to have anything that's over here bonking into all the stuff on the boron. Okay, so we're going to go here and here. So this is our syn addition. Helps if I draw on the H, and then I get a little more confident about what I'm drawing. Okay, so then I still have those 2 on the boron. So you can think about it like this, or think about 2. I mean, I can also just draw it out so that you, not so hard to do. There we go. So you have that right now with the alkene there, which I almost forgot. So that is your hydroboration step. The second step with the oxidation is going to be the exact same. So you're still going to have your hydrogen peroxide, your water, your sodium hydroxide. All of that stuff is still the same. And that process is still the same. And then look what you end up making, another enol. Okay, if we think about what this enol is going to turn into, we have an H right here. So that is going to end up turning into an aldehyde because we've got one carbon and one H. But we have to think about the fact that right now we're in basic conditions. So we're not going to be doing anything like this. Oops, we're not going to be forming any positive charges here. We're going to be forming negative charges or neutral molecules. So if I want to end up getting, oops, eventually to this aldehyde, then I know that I need to add an H here, and I need to get rid of the H there. So the process, or at least what I need to do, is still the same, but the order of that is going to be slightly different. So just like we deprotonated this last, since we're in base, we're going to deprotonate it first. Since that is our most acidic proton here. Okay, we're going to get to this. This is actually an enolate because it's now negatively charged. Okay, now we can start going forward and getting our alkene protonated. So the only acid that we have around is water. So we're going to reform our carbonyl, or form it in the first place, I guess. We're going to go grab a proton, make more OH minus, and that gets us to our aldehyde with the two H's right there. Okay, so that's one way to make ketones and aldehydes with the hydration reaction of alkynes. These are going to be the two ones that we use pretty much the whole time. So the one with water, sulfuric acid, and the mercury catalyst, and the hydroboration oxidation to get the aldehydes. Okay, so then our last reaction that is special to alkynes is alkylation reactions. So if I have, and again, this is going to be terminal only. Okay, so we pretty much have one option that can work on anything, one option for a hydration that can work on anything, but you wouldn't want the internal ones. And then the alkylation are only terminal alkynes, okay? And you'll see why in a second. So this is one that I know that at least my class did quite a bit last semester when we were talking about SN2 reactions. And that is to use alkynes as a strong nucleophile. So if I add a base, so sodium amide is commonly used. You can also use sodium hydride. Okay, both of those are going to be strong enough to do this. And if we deprotonate, remember those alkyne H's have pretty low pKa for a carbon because we've got that sp orbital, which has more s character. It's got more of that electron density closer to the nucleus. So that is a very special feature of alkynes. You cannot do this with alkenes. It is not at all acidic enough. Okay, so once we have that strong nucleophile, then we can just go ahead and add in whatever good electrophile we want. This pretty much has to be limited to primary alkyl halides generally, just because you can get a lot of E2 stuff going on if you do a secondary. So we can attack our electrophile, kick off our leaving group, and now you've added carbons to your alkyne, okay? So this is a really powerful method because we just were able to make that carbon-carbon bond, and making carbon-carbon bonds is actually fairly, as much as it may not seem like it, it can be a very difficult thing to do, and doesn't happen in every single reaction. So it's a good thing to keep in your head. All right, so we'll be talking about this for the week. And please ask any questions you have, and I will see you all later.